Hi, I'm going to tell you about primordial parity violation from inflationary loops, and this is based on work with Gordon and Enrico. So in particular, I'm going to describe a parity-odd scalar correlation function in single clock exactly scale invariant inflation. Parity violation in scalar correlators can first show up at 4 points for kinematic reasons, and in fact, thanks to a no-go theorem, this parity-odd trispectrum in this scenario starts at one loop. There is no tree-level contribution. So what we're going to do is calculate this trispectrum and then check whether the trispectrum can be observably large. First of all, though, I'll say some words about motivation, why we would want to calculate such a thing. One point is that in 2022 there was this interest in possible parity violation in the trispectrum, the 4-point correlation of boss galaxies. So it's interesting to ask how you can generate parity violation in the large-scale structure, and one way of doing it is during inflation. This is not a completely crazy thing to imagine, since we know that parity isn't a good symmetry of the standard model. The electroweak sector breaks parity explicitly, and so it's also possible that parity may be a broken symmetry during inflation. The other point is that since the no-go theorem tells us, which I'll describe later, tells us that this correlator has to start at one loop in this scenario, it's a model in which quantum effects during inflation can possibly be observably large. The point is that tree-level correlators are semiclassical, whereas loop effects really represent quantum fluctuations about the semiclassical trajectory. First of all, before that, some words on inflation itself. Inflation is a period of almost de sitter expansion in the early universe, and since I'll be looking at the limit of exact scale invariance, this is going to be a period of exactly de sitter expansion. So that means that the space-time is described by this metric, where the Hubble parameter h is in fact a constant, and eta is conformal time, which starts at negative infinity at the beginning of inflation, and it goes to 0 at the end of inflation. This de sitter spacetime has the usual homogeneity and isotropy, and it has an additional symmetry, which is scale invariance, which looks like x goes to lambda x, and eta goes to lambda eta, and k can go to 1 upon lambda k, where k are the Fourier modes of some field that we're considering. Now, one field we can consider is the primordial curvature perturbation zeta, which is modelled by a massless scalar living on this de sitter spacetime. And it's interesting because the things we observe in the late universe, like the overdensity of galaxies and the large-scale structure, and the perturbations in the CMB, are given approximately on large scales by some transfer function in Fourier space, multiplying the Fourier modes of this zeta field. So if we want to understand correlations of the large-scale structure, and we understand the transfer functions, we just need to understand the correlation functions of this zeta. So, how do we calculate those? One way we can compute correlations of quantum fields on curved spacetime, here I'm choosing some generic field phi, is using the in formalism. We can compute an equal time correlator and some time eta naught by starting with some state in the asymptotic past, time evolving it to some finite time, to this finite time eta naught using a time evolution operator, and then just finding the expectation value of this product of fields as in normal quantum mechanics. And we can expand each of these time evolution operators as some time-ordered exponential of some interacting Hamiltonian. Then we can quantize this field and expand all of these terms out. We quantize the field just by writing each Fourier mode in terms of creation and annihilation operators, and multiplying each of these by some solution of the free equation of motion of the field. We select this free equation of motion by choosing the Bunch-Davies vacuum normally, which means that in the asymptotic past, as eta goes to negative infinity, these mode functions, these fk's, just look like massless mode functions living on flat spacetime. They look like some scaling times e to the negative ik eta. Since we'll be doing some loop integrals later, and I'm going to do them in dimensional regularization, it's useful to have these mode functions in not just 3 spatial dimensions, but 3 plus delta. And in fact, the regularization prescription I'm going to be describing is going to modify the mass of the field slightly away from delta equals 0 to keep the mode functions in a particularly convenient form. But in general, remember throughout that delta equals 0 means exactly 3 dimensions, and so the final answers are going to be evaluated at delta equals 0. And we can expand these time evolution operators with the interacting Hamiltonians in terms of field operators, products of field operators, and then contract them either with the field operators in the correlator we're trying to find, in which case we have one particular kind of propagator, or we can contract them with one another, in which case we have some other propagators. The point is that we have two time evolution operators, and fields can be contracted within the same time evolution operator, between different time evolution operators, or with these other fields, and so we get a lot of propagators in the Indian formalism. Finally, I'll say a few words about the no-go theorem, which says that the parity-odd scalar trispectrum vanishes at tree level in theories which contain only scalars, or which contain scalars and fields of any spin as long as they have only massless or conformally coupled mode functions under Sitter. As long as the theory has exact scale invariance, the interactions don't become infinite at late time, and the vacuum is this Bunch-Davies vacuum I described earlier. In fact, we know that scale invariance isn't a perfect symmetry of the early universe, so we might expect that this is one of the other places that parity violation in the scalar trispectrum might show up. As for the calculation, I'll start out with a simplified example, which is going to involve 6 different conformally coupled scalars. They're conformally coupled because these ones have simpler mode functions than the massless scalars, and there are 6 different fields, so that we don't need to sum over all permutations of the external kinematics. This just means that we can choose slightly simpler interactions without getting a vanishing result. Since this is a two-site loop diagram, this is the simplest non-vanishing loop diagram, we need 2 operators to give rise to the interaction. One of them is going to need to be parity-odd and one parity-even, so that the final answer is parity-odd. And so these are minimal choices of the 2 operators. The integral corresponding to this interaction looks like this. It's mildly complicated, although I've elided some details. The important point is that in exactly 3 dimensions, when delta is 0, the integral is manifestly real. You can see this just by rotating the contours of the time integrals, and because every eta inside these square brackets is accompanied by a factor of I. However, at delta equals 0, the integral is also manifestly divergent. And so what we can do is, since the parity-odd correlator is imaginary, we can expand after performing this rotation these 2 delta-dependent functions in delta, and what we end up with is that the parity-odd part of the trispectrum is given by some part proportional to delta, which vanishes as delta goes to 0, multiplying the 1 upon delta divergence from the rest of the integral in dimensional regularisation, so that the overall result is negative 2 by I times the residue of the 1 upon delta divergence. And so when we compute the integral, we just need to get the residue of the 1 upon delta divergence. Now, of course, this is kind of subtle because dimensional regularisation involves some complicated analytic continuations. We need to be sure that we're not doing something wrong by cancelling this divergent piece with this vanishing piece. And so indeed we've verified that we get the same result for this integral in cutoff regularisation. For the full interaction, which I'll discuss in a second, we did not verify in cutoff regularisation, but it's unlikely that there's going to be any new complication. Anyway, one can do this integral, one can do the time integrals first and then the momentum integrals, and the result looks like this. So I'll talk you through some of its properties. This vector structure, of course, is there because it's parity-odd. This e to 0 to the 4th power is because the conformally coupled fields are massive, and so at late times the correlator is decaying. This integral takes the form of a rational function. S is just the vector sum of the k1 and k2 momenta flowing into the left-hand vertex. K12 is just the scalar sum k1 plus k2, the sum of the lengths of the vectors. Similarly for k34, and k total is just k1 plus k2 plus k3 plus k4. So one interesting thing about this rational function is that it's singular only when any of the individual k's go to 0, or when k total goes to 0, if we make some analytic continuation. Generically, for an exchange diagram, you would expect other kinds of singularities, for example 1 upon k12 plus s. This would be a partial energy singularity. In fact, these don't appear. The other interesting property is this isn't zero. This is good, otherwise we would have to do a more complicated integral. But it's also not infinity. If it were infinity, that would also be bad. The reason for that is that the no-go theorem I mentioned earlier says that you cannot have a tree-level interaction that gives rise to a parity-odd 4-point function in this scale-invariant single-clock scenario. So the point then is that if this were divergent, like 1 upon delta, for example, 1 upon the Dirac parameter, which would be like a logarithmic divergence in cutoff regularisation, we wouldn't be able to reabsorb the divergence into counter terms in the action. So although we don't have a mathematical proof that this always happens for parity-odd trispectra in this case, it seems hard to believe that the result could have been anything else in particular. The result could have been divergent. That would seem to be unphysical. So, having understood what the calculation looks like in the simplified case, we can try to do the full calculation. So now we have some more complications because we're going to do massless fields rather than conformally coupled. The mode functions are a little bit more complicated. There will be more terms in the integral. And we have to sum over all permutations of external kinematics. There's some technical requirement that we want to be able to embed it in the effective field theory of inflation without generating a bispectrum. What this essentially means is that we need to pick operators where compatibility with the symmetry breaking pattern of inflation doesn't generate other kinds of correlations like a bispectrum, which are experimentally constrained separately. This is a requirement to ensure that we can try to make the correlation big, that we can try to make the signal big. So it turns out that a minimal choice of interactions that have these two properties are these. For the parity-odd vertex, we now have a dimension 13 operator. This turns out actually to be the smallest parity-odd operator in a single field. That's not zero. And in the parity-even case, we have something a little simpler. It's still a dimension 10 operator. And the choice of this is related to not generating a bispectrum and related to having the correct index structure on the loop to give a non-vanishing result, as in the correct set of derivatives on the loop to give a non-vanishing result. I'm not going to talk through the details of the calculation. I'm also not going to show the result because it's quite complicated to the extent that it would be difficult to get anything useful out of inspecting it. So as I say, it's exceedingly messy. However, it has some good properties. It's still a rational function, like the one we saw before. It doesn't have partial energy singularities. It only has total energy singularities. And it's not zero, and it's not infinite. So again, we're not in trouble with having to renormalize the 1 upon delta divergence, where we can't absorb the divergence into any contact counter term. And it has this scaling. We imagine that lambda is going to be bigger than Hubble, each of these two lambdas, which are suppressing the two operators. So numerically, this trispectrum is going to come with a small number attached to it. Now, the small number turns out to be a problem if you want to estimate how large the signal can be, and that's because this parity-odd one-loop trispectrum is made out of two operators. One of them is a parity-odd quartic operator, and that's not going to generate a contact trispectrum by the no-go theorem. On the other hand, the other operator was a parity-even quartic operator, and that is going to generate a contact parity-even trispectrum. And basically it's going to come with some Hubble over lambda parity-even suppression, and then it's going to have this same kind of general scaling. So in a cosmic variance limited experiment, where the noise in the parity-odd and parity-even channels is the same, the relative signal to noise in this parity-odd one-loop trispectrum versus this contact trispectrum that we also had to include in the theory is going to look roughly something like this. So this is Hubble over some larger scale associated with the parity-odd channel, parity-odd operator, which is going to be a small number, then some other small number corresponding to the fact that this one is at one loop, whereas this one is contact. So we would generally expect to observe the parity-even operator, the parity-even trispectrum first. It might be possible, one might think, to boost the size of this operator with more derivatives by turning down the speed of sound of the curvature perturbation, but although one does end up generating some 1 upon sound speed factor, overall this number still needs to be small, and that's related to requiring that the theory is not strongly coupled around horizon crossing. So unfortunately, although we've found an interesting quantum effect in the early universe, and we've shown that it has some interesting analytic properties as a finite rational function, and maybe it would be interesting to understand why. We've also shown that its signal to noise is typically going to be bounded above by some other parity-even correlator, and it's interesting to ask whether this always happens, because, for example, even if we had some way of generating a parity-odd trispectrum without including a parity-even operator, actually then two parity-odd correlations may be put together to make some kind of parity-even correlation. So it would be interesting to get a better understanding, maybe even non-perturbatively, of the interplay between the parity-odd sector and the parity-even sector. Thank you for listening.